Hello, Accelerated Chemistry students. This is Ms. Crisafulli, and this is your Chapter 11, Section 1 video notes all over describing chemical reactions. So all chemical reactions involve changing substances. So in a chemical reaction, one or more reactants is going to change into one or more products. So chemists use a chemical equation, which is a short, quick hand notation, to convey what is happening during the chemical reaction. So they could write word equations, and word equations are used to describe what's happening in the chemical reaction. So the reactants are written on the left and the products are written on the right, and an arrow is going to separate them. The arrow means yields, gives, or reacts to produce. So again, reactants are going to go on the left, then our arrow, and then products go on our right. So when we're writing word equations, we're going to write the names of the reactants to the left of the arrow, and we're going to separate each of those reactants, if there's more than one, by a plus sign. And then we're going to write the names of the products to the right of the arrow, and also if there's more than one of those, we're going to separate them with a plus sign. So let's look at this example. Iron reacts with oxygen to produce iron 3 oxide. So iron is going to go first, plus, because it says reacts with oxygen, produces, that's your arrow, remember, and then iron 3 oxide. It's pretty simple when we're writing word equations. A chemical equation is a representation of a chemical reaction. The formulas, not names, of the reactants are written on the left, and they're connected by an arrow with the formulas of the products, which are going to be written on the right. So let's look at that equation that we just looked for making iron 3 oxide, which is rust. So iron plus oxygen gives iron 3 oxide. So this is the form that we're mostly going to be using in class. Equations that show just the formulas of the reactants and products are called skeleton equations. A skeleton equation is a chemical equation that does not indicate the relative amounts of the reactants and products. So in the first step for writing a complete chemical equation, we're going to write the skeletal equation first. So that's just our elements. So Fe, iron plus oxygen gives iron 3 oxide. So to write, one more time, a skeletal equation, you're going to write your formulas for the reactants on the left side of the arrow, and you're going to separate if there's multiple reactants with a plus sign. And then you are going to write the formulas for your products on the right side, and if there's more than one product, you're going to separate them with a plus sign as well. So then you need to add the physical states of substances, and you are going to add them by adding symbols after each of the element formulas or compound formulas. So S is a solid, L is a liquid, G is a gas, AQ is aqueous, which remember means a substance that is dissolved in water. And so for our equation that we've been writing for the last few slides, it's iron solid plus oxygen gas to make iron 3 oxide solid. So in many chemical reactions, a catalyst is going to be added to the reaction mixture. A catalyst is a substance that speeds up the reaction, but is not used in the chemical reaction. So it's not either going to be a reactant or a product. And so how we denote that is we write the formula of the catalyst above the arrow in the chemical reaction. So let's look at hydrogen peroxide when it decomposes. When hydrogen peroxide decomposes, it's a very slow process. So we're going to need to use a catalyst in order to speed it up. So hydrogen peroxide decomposes to water and oxygen gas. And the catalyst that we use is manganese 4 oxide. And so we denote that we're using a catalyst by writing a manganese 4 oxide formula over the arrow in the chemical reaction. So let's look at a sample problem. So let's write a skeletal equation. So hydrochloric acid reacts with sodium hydrogen carbonate, which is a solid, and the products formed are aqueous sodium chloride, water, and carbon dioxide. This is where your formula naming and writing skills are going to come into play. So let's write the correct formulas for each substance in the reaction. We're going to indicate the state of each substance. We're going to separate the reactants and products by using an arrow, and we're going to use plus signs to separate the reactants and the products. So let's start by naming. So our reactants are sodium hydrogen carbonate, and that's a solid, hydrochloric acid, which is aqueous. Our products are sodium chloride aqueous, water, which is a liquid, and carbon dioxide, which is a gas. Now what we need to do is we're going to need to change these names to formulas. So sodium hydrogen carbonate solid, hydrochloric acid. Our products are sodium chloride aqueous, water is a liquid, and carbon dioxide as a gas. Now that we have all of our formulas and they're written correctly, now we can put them into the equation. So we are going to set up our equation, reactants on the left, products on the right. Each reactant is going to be separated by a plus sign. Each product is going to be separated by a plus sign. So we have sodium hydrogen carbonate as a solid, plus hydrochloric acid, aqueous, yields sodium chloride aqueous, plus water as a liquid, plus carbon dioxide as a gas. Pretty self-explanatory. You have to make sure that you know how to name these formulas. Remember, we've talked about it in the past. We did a lot of naming practice in chapter 9. I know it's been a couple chapters ago, but you might want to go back and look that over again. So now let's talk about the law of conservation of mass. The law of conservation of mass allows for us to write chemical reactions appropriately. And there is, when stuff is being mixed together, there is a conservation of mass, energy, and charge. So what goes into the reaction must comes out. So the number of atoms in each element must be equal on both sides of the equation. And so remember, the law of conservation of mass and energy states that matter and energy cannot be created nor destroyed. It will only change from one form to another. So when we are looking at the conservation of mass, an unbalanced chemical equation does not have that. So if we look at the synthesis of water, we have hydrogen plus oxygen gives us water. If we were to look at the mass of these, hydrogen has a mass of 2, oxygen has a mass of 32, and water has a mass of 18. If we were to look at those things, we would see that these two masses on the left and on the right side of our equation do not add up to be the same. So they do not show the law of conservation of mass. If we balance the equation, however, that is, put coefficients in front of our formulas or in front of our compounds in our equation, that actually will show that we conserve mass. So let's do that. So if we have 2 hydrogen, 1 oxygen, and 2 waters, and we were to look at the masses now, they do equal each other, which is 36 grams each. That shows the law of conservation of mass. So in order to do that in everyday scenarios, we have to balance our chemical equations. So first we're going to do is we're going to total up the elements on each side first. And if we have polyatomic ions, we're going to keep them together. We're going to start with the element that is only found once on both sides, and we're going to place a coefficient to balance that out first. We're going to keep polyatomic ions together, and we're going to count them as a unit if not broken up on both sides. And the coefficients at the end, after we're done balancing, need to be brought back down to the least whole number ratio, meaning that they need to be reduced. And then we're going to check to see if it's balanced at the end. So let's go through a couple examples. So here's our equation. First thing I'm going to do is I'm going to list out my elements. And I list out my elements in the order that they appear on both sides of the equation. Okay, so aluminum, copper, and chlorine. Now what I'm going to do is I am going to put a big line down the middle separating my reactants from my products because I want to keep them totaled separate on my left side and on my right side of my reaction. The total needs to add up on both sides to be the same number. However, I want to keep track of them separately. So first thing I'm going to do is I'm going to write down how many of each element I have on the left, and then I'm going to write down how many of each element I have on the right. So on the left, I have 1 aluminum, 1 copper, 2 chlorines. And on the right, I have 1 aluminum, 1 copper, but 3 chlorines. So now when I'm looking to see what I want to make balance, I need to balance my chlorine. So let's go through that process. I'm going to put a 2 in front of the aluminum on the left, which is going to change my total to 2 on the left. When I do that on the left, I also have to do that on the right. So that changes that total to be a 2. But since it is in front of both the aluminum and the chloride in aluminum chloride on the product side, I have to distribute that coefficient of a 2 not only to my aluminum, but to my chlorine as well. And when I do that, now I have 6 chlorines. So now I'm going to go on the left, and I'm going to balance my chlorines on the left. So I'm going to make sure that I have 3 chlorines a coefficient of 3 needs to be added. So that means I have 3 coppers now and 6 chlorines on the left. And on the right-hand side, I put a 3 in front of copper. So now I have a 3 copper on the right. So now when I look at this, everything is balanced. I have 2 aluminums on each side. I have 3 coppers on each side. And I have 6 chlorines on each side. Works. Let's look at another example. So again, split down the middle. I listed the elements on either side. 2 nitrogen, 2 hydrogen, 1 nitrogen, 3 hydrogen. I'm going to balance my nitrogens first. I'm going to put a 2 in front of the nitrogen on the right. That changes my total for my nitrogens, and it changes my total for my hydrogens. Then I'm going to put a 3 in front of the hydrogen on the left, and that makes 6. So now on each side, I have 2 nitrogens, and on each, I have 6 hydrogens. So now we're good. Last one. Let's look at this one. 2 hydrogen, 2 oxygen, 2 hydrogen, 1 oxygen. I'm going to balance for my oxygens on the right, which is going to make that 2, but it also changes my hydrogens to a 4. And then I'm going to balance my hydrogens on the left, and that makes that 4. So now I'm balanced. 4 hydrogens on each side, 2 oxygens on each side. Perfect. So we're going to do lots of balancing in class. So I want you to keep practicing on this. All right. And as always, all the information on these Google Slides has been acquired and adapted from Pearson Chemistry's 2012 edition of the textbooks, resources CD, and pearsonchem.com. Thank you so much. Have a good night.